Hello, this video is on examples of groups coming from matrices, groups of matrices. So really the starting point is, as very often in group theory, is the story of symmetries of some algebraic object, of some mathematical object. In this case, it is a second sort of standard mathematical object, a vector space. The first would be a set. And then the group of symmetries will be of such vector space will be a collection of all invertible linear maps from the vector space to itself. And such linear maps are called linear operators. If they start and end in the same vector space. And on top of that, we just assume them to be invertible, so that under composition, they will form a group. This group is called the general linear group of the vector space V. And the promise was talk about groups of matrices, and they appear if we take as a vector space the vanilla example vector space of a field, say field F. If we take coordinate vector space of finite dimension n, and in this case, linear operators using the standard basis of this vector space can be recorded as matrices, as square matrices, and invertible would just translate to invertible matrices. So the automorphism group of this finite dimensional coordinate vector space will be just a set of all invertible square size n matrices. And the notation used for this version of the general linear group will be general linear group of matrices of size n with coefficients in F. The sort of standard notation for the collection of all matrices of square matrices of a given size is m sub n, and then the coefficients in brackets. And the group operation of this group is the product of matrices. The product of matrices is just the record, the translation of the composition of linear operators into a matrix form when we write the matrix of linear operators. The condition of invertibility can be replaced by a certain polynomial equation on the matrix, namely the condition that the determinant is non-zero, and the determinant itself is going to be a function on the invertible matrices, if we like, with values in numbers, and then the multiplicativity of the determinant is the statement that we have a homomorphism into the multiplicative group of our field, and the notation for that multiplicative group is F with a cross, so that will be just a collection of all scalars but not zero. Under multiplication, they will form a group. So the determinant is a homomorphism. A group homomorphism. And then the alternative notation for this set of conditions that we look at invertible square matrices will be just this self-builder version. We have square matrices with coefficients in F, and then the determinant is invertible. If F is a field, then it is equivalent to being non-zero, but in general, if F is, say, a ring of integers, invertibility is a proper condition. So the homomorphism we can analyze further. We can look at how is it surjective, and the answer is yes. Surjective means that any element in this group is the image of something in this. So in plain words, it will be just saying that for any scalar, non-zero scalar, there should be a matrix with the determinant being just this number. And one example of such matrix would be just to take this number, put it on in the first position of the diagonal, and the rest of the diagonal populate with ones. Everything else is zero in the matrix. The determinant of such diagonal matrix will be the product of diagonal entries, so it will be just our number. So the determinant is onto is surjective. In terms of graphical notations, it's just double arrowhead for the arrow of the homomorphism. And we can look at the kernel. And the kernel in general, for say the size of matrices being bigger than 1, is going to be non-trivial. It will consist of all matrices which have determinant 1. So just literally the definition of the kernel. And the compact notation for this normal subgroup of the general linear group is this. It is SLN with coefficients in F, and the name is a special linear group. So that is the sort of first two standard linear groups coming from standard examples of groups coming from linear algebra. If we look at more than just a vector space, if we take more than just a vector space, if we assume some additional structure on the vector space, we would get some smaller groups, subgroups of this general linear group, which will still be possible to describe as group of matrices. One example is just to imagine a scalar product, a bilinear function on a vector space. And then we could collect all symmetries of the vector space which preserve this function, namely assume that we have this equation for all vectors u and v. So that would be scalar product of vectors which are moved with the operator g, and the result of this move, the scalar product of, will be the same as before the move. The collection of all such, again, will form a group, a subgroup of the general linear group, and the usual name for this is the orthogonal group. To define, we use a vector space and this scalar product, so it is orthogonal group of that pair. And the sort of most frequent example, the standard example, if we assume our vector space to be the coordinate vector space of dimension n, and define the scalar product by this standard formula. So the scalar product is in charge of measuring distances. If our field is the field of real numbers, in this case it is called Euclidean. Product or dot product. And the orthogonal group of that scalar product is just the standard matrix orthogonal group. And if we replace operators by the matrices in this standard basis we have in the coordinate vector space, we will have square matrices. The condition of preservation of the of this Euclidean product, it is very easy to see. It is just the matrix equation that the matrix times its transpose is the identity. So that will be the matrix version of the orthogonal group. And as before, we could look at determinants as determinant as a function, as a homomorphism from this group into the multiplicative group of the field. And it is easy to see that the image is now not the whole thing, but rather a very small subgroup of it. The image will be just two-element subgroup consisting of plus and minus 1. And this is a consequence of the multiplicativity of determinant plus this defining condition for orthogonal matrices. And the one extra fact that determinant of the transpose is the same as the determinant of the matrix. So if we just take the determinant of both sides of this equation, we will have we'll quickly reduce it to this equation that the determinant squared is the determinant of the identity matrix, which has to be 1. So there are only two possible determinants. And that really is the key, again, in the case of the real numbers, is the key to define orientation preserving and orientation reversing transformations. So there will be orientation preserving if they have the determinant 1, and orientation reversing otherwise. And you could look at examples. Rotations will have determinant 1, reflections will have determinant -1. So the finally the special orthogonal group will be just the subgroup of the orthogonal group or the subgroup of the special linear group, which will be just defined by the pair of conditions, this time orthogonality plus the condition that determinant is 1. So that will be orientation preserving maps if the field of coefficients is real numbers. In general, this is just called the special orthogonal group. So that's it for this video. See you later.